And Sirki gets everything right. So key ideas we're going to be using here, the notion that momentum is mass times velocity, and that change in momentum, another word for which is impulse, is a bunch of stuff. So number one asks, how much momentum does an 80 kilogram mass have if it's traveling? How much momentum? Momentum is mass times velocity. It's going to be 80 times 22. 160 plus 32, 192? No, I'm way off. Hang on. 1,600, Mr. Duick, plus 160, 1,760. Yep. Yeah. Forgot to carry a zero there. Units, kilogram, meters per second. 1 mark for the answer, half mark off if you got the units. Now, number 2 is asking for a change in momentum, an impulse. My first step typically is to say, well, that's that, and now I'm going to plan my attack. How can I find impulse? One way to find it is force times change in time. Actually, I rejected that, Matt, because I glanced at part B, and I noticed part B is asking me to find the force, and if they're asking me to find the force, then there's no way I can use the force. Not even Yoda. So I can't use the force here. Then I said, did they give me a final and initial velocity? Hey, this is where I'm going. I'm going to use the idea that it's m change in velocity, except I'm not going to write it that way, because what's change in anything? Final mass. So instead, I'm going to go mv final minus mv initial. The mass is 220. Looks like the final velocity is 52. I did a quick check. I don't think, Geo, there's any change in direction. I don't need to let one way be positive, one way be negative, but I'm always keeping my eyes open for that. You better. There's going to be questions that we deal with like that. 220 times 23. Do this one in your head, Mr. Duke? Well, maybe. 52 take away 20 is 42. 220 times 39. 220 times 4. Yeah. I think I could, but I'm not going to worry about it. Do you get, why negative, Mr. Dewick? Because I typed a negative instead of a times sign there. Let's try that again. Do you get 6,380? Yep. Units? Yep. And again, I would also accept Newton seconds, because that's also what it is, but I used mass and velocity, so I'll go with that. B says, what's the magnitude of the force? Again, I could find, don't write this down, I could find the force by going F equals ma and then going A equals Vf minus Vi over T and sticking it all into there. But the fact that I have the impulse gives me a nice shortcut. I can say impulse equals force change in time, which means that force equals the impulse times the time. We equals 6,380 divided by 58 seconds. And I get an average force of 110 newtons. 1 mark. Number 3 is asking me to find the impulse. That's also the change in momentum. So the first thing I start out with is I write that down, delta P. You know what? Since part B is asking me to find time, I don't think I can use force times time to do part A. I think, again, I'm going to say it's m delta V, except change in anything is final minus initial. And I think in this case, the final momentum is 0, because it says brought to rest. So it's going to be 0 minus 80 times 110. 8,800? Negative, sorry, negative 8,800? No?
It's a different 3A not.
Oh, it's not 80? It's not 110, Mr. Wow, where'd that 110 come from? I'm looking up here. 18, Mr. Dewick. 110 meters per second on a skier would be pretty fast, possibly terminal. So it's going to be 800 plus 72, negative 872? No, 864. Wow, I'm way off. Negative 860. Am I still off?
1440.
Wow, Dewick. I'm in a slump here, clearly. Negative 1440. How could I not get that? Kilogram, meters, per second. What's the negative telling me? You know what? To come to a stop, you have to lose momentum. So I will be fussy. The negative does have to be there. In other words, if you're traveling forwards, the change in momentum is backwards when you're coming to a stop, which makes sense. How long should this force act? So I'm going to say, well, now impulse is force times time. This time we're going to get the time by itself. I guess the time is going to be the impulse divided by the force. It's going to be negative 1,440 divided by 270. Now, if you do this, you're going to get a negative answer. Time, scalar or vector? How can I make this positive? The force is also negative because it's pushing in the opposite direction. It's actually technically a negative times. Now, if you didn't put the negative in, but at the end you said, I know time is a scalar, and you wrote a positive answer, Ira, I'll be okay with that. If you wrote a negative time, I would take a half mark off. So it's going to be this number divided by negative, I think this will work out evenly. Or count on nice, 5.3 seconds. Give me 1 second to pause the video there. So again, if you actually let time be negative, I would take a half mark off because it's a scalar, okay? And there's the reason why you should get a positive answer, because it's a negative impulse technically times a negative force, 1 mark. Turn the page. Oh, now we're into 2-mark questions. Okay. Why 2 mark? I'll bet you there's a change in direction. I see east, I see west. I'm going to let one way be positive, one way be negative. How many of you love working with negative numbers more than positive numbers? How many of you would rather work with negative numbers? You? Okay. You can do it your way. I'm going to give you a little trick. Typically what I do is I let the final direction be positive. I'll show you why. So I'm going to let west be positive. I'm going to let east be negative, and you're going to see why in just a second. It wants me to find the impulse. Well, impulse is change in momentum, and I think I'm going to use mv final minus mv initial. The reason I figured that out is I glanced at part B and I said, oh, they're asking me to find a force, so I'm not going to do it that way. The mass, 0.17, because it's grams, not 170 kilogram hockey puck. Please, you're Canadian, you should at least know that much. That's okay.
Sorry.
That's okay. West, positive 43. You don't need to put the plus sign in there. I'll just put it in my notes so that you know, John, I thought that. Minus 0.17. East, negative 22. Do you see why I let initial be negative? Because I get a minus minus, which is a... I'm less likely to make a dumb mistake with positive numbers. Little trick of the trade. You don't have to. You could let east be positive always and west be negative always, and there's some value in that because that's kind of what we're used to, and that way you won't trip on your brain. And I totally respect that method too. I'm just a nerd and I don't like negative numbers that much, so I'm going to get rid of it. And I get an impulse of you get 11.05? Kilogram meters per second direction. Now, I didn't specifically say in this question, give the direction, so I guess I can't take off a half mark if you didn't say a direction. I should have said in brackets, next to the word impulse, magnitude and direction, and I did not. But you should make sure that your 11.05 has the same positive or negative as whatever you let west be. If you missed the change in direction, you would have ended up with something like this. With a minus, you would have ended up with 3.57, I think. I would only give you 1 out of 2 for that. Is that all right? Sound good, Gio? Gio, what does B want me to find? Yeah, I caught you mid-yawn, I know.
What is the average force?
Average force, what did I find in part A? I bet you there's an equation that has force and impulse in it. Impulse equals force change in time. Now, I'm committed for this question with my specific direction convention. If I get a positive force and west, if I get a negative force, There you go. If you did it the other way around, perfectly fine as well. Just be consistent for your question. I think the force is going to be impulse divided by time. It's going to be 11.05 divided by 0.025. That's a small amount of time. I think this is a slap shot, so shouldn't be much time. 11.05 divide... Oh. You get 442 newtons, which seems about right. I would imagine getting hit by a... Is that right? Am I wrong? Yes? Okay. That seems about right also, Elliot. I imagine if somebody hit me with a hockey stick, it would hurt, and something in the 500 or higher newtons hurts. So a gut instinct. Not quite as hard as a baseball, but that also makes sense because when you hit a baseball, that's going a lot further. A hockey stick slap shot will not leave a ballpark the way a baseball will. Yes?
Oh, never mind. Okay.
I figured so. That's why I ignored you for a while. Okay. If you wanted to add a direction, for me, west, I think on the test I would probably say magnitude and direction. In fact, I'm making a mental note to retype this quiz and add those phrases to it. Ah, there you, I knew I would have in part somewhere there. We have a baseball, 150 grams, that's 0.15 kilograms, nice try. Thrown due east, due west, okay. I'm gonna let west be positive, I'm gonna let east be negative. Again, you could do it the other way around, but my rule of thumb is I tend to let the final be positive and the initial be negative. Once the impulse, so impulse is gonna be, you know what? I think I'm gonna use this one. How did I know to use that one? Because what's part B asking me to find, Tato? Well, I better not use MV final minus MV initial. And I scanned quickly. I saw newtons and I saw seconds in the question. This is why I've told you it's worth memorizing the units. It really lets you glance at a question and plan your attack out pretty quickly. So force. What direction would the force be? I think the force would also be in the west direction. So I'm going to call it positive 20,400. Time 7.5 times 10 to the negative 4 seconds. So 20,400 times 7.5 times 10 to the negative 4. Do you get an impulse of 15.3? And I'm going to write Newton seconds, but if you wrote kilogram meters per second, totally fine with that. Find V final, 3 marks. Okay. I think I'm going to use the idea that impulse equals mv final minus mv initial. They want me to get v final by itself. I think the first thing that I would do is the delta p will drop down like a domino, and I'll plus not final, mv initial over. That would give me mv final. I think I'll divide by m. V final is going to be the change in momentum, 15.3. Now, if you got a different answer for part A, but you dropped that number down here in part B, I will give you full marks if you did your version and got your correct answer relative to your impulse. Plus, I don't need to multiply that by the time or anything, m.15 negative 39, right? Divided by 0.15. 15.3 plus 0.15 times negative 39 divided by 0.15. Do you get 63? Yeah? 63 meters per second. That's the magnitude. Direction, for me, positive, is west. If you weren't careful with your directions, if you did that, I would give you, if you said the answer was 141, I would give you 1.5 out of 3. Okay? In terms of part marks, I would give you 1 mark if I saw that, 1 mark for that, half mark for the number, and a half mark for the direction. Can you give yourself a lovely score out of 13, please? And then can you make sure your name is on them? Can you pass them in? So your lesson 2 homework is due today. If you still have questions about impulse, you'll have to hit me up during a flex block because I want to get a big chunk of this done.
Listen to the two-step.
Yep. Yep. By the way, lesson 2, lesson 3, and we're done. Your test is not going to be next week, but it will be the week after. We're kind of in the home stretch here, so not many classes left. Yeah.
Do we have a unit after this?
Yep.
Okay. Is that the last one?
I think so. Collisions and conservation of momentum. Says this, in the collision seen below, which vehicle experiences the larger force? You know what? Once again, this is a chance for us to vote. Once again, how high you hold your hand up, so how sure you are of the answer. So we have a big truck, a little car. Which one experiences the larger force? Who says the truck experiences the bigger force, Mr. Dewick? The truck, the truck. Who says the car experiences the bigger force, Mr. Dewick? The car, the car. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Who says they're both the same? 2, 3, 4, 5, 6, 7, 8, 9, 10. Who's right? Rick, why is the same correct? Why is that correct, folks? Yeah.
Of course, it's not fair.
So why did you vote the other way?
I wasn't thinking.
So this is Newton's third. Okay? Newton's third. Forces come in pairs. Pairs. Forces come in pairs. The force between these will be identical. The damage between them will not be the same. And that's because there's different masses involved, which means different accelerations are involved. And really, when it comes right down to it, what does the damage is not the force, it's not the impulse, it's the acceleration. It's the acceleration. The change in velocity. So, why is it that the car and driver are almost always worse off? I just kind of said it. Sasha, what were you going to say? Do they both have the same force?
Yeah.
Do they both have the same force? Yes? Okay, you know what? Let's go like this. Let's draw a little line down the middle. Let's go real basic. Sasha, F equals what? Big M, small acceleration, little m, big acceleration, and then you can make a little note here. Acceleration is what does damage. Now, the force is heavily related to acceleration, which is why typically we say, well, the force, getting hit by a big force hurts, but the reason is also because it's trying to accelerate you. Alec, you okay with that explanation there? We've done the small letters and big letters before, I think. I need to give you a terminology. A closed system is one that is cut off from the outside world. And this means that there are no external forces. There's no applied force off the screen giving something a push or a pull. Examples of those would include frictionless systems, like ice, or floating on water, because when you're floating on water, that's nearly frictionless. Systems in deep intergalactic space. Rolling objects. Okay. So, closed system, no external sources of energy, no external sources of forces. All right. For collisions in a closed system, the impact forces, the contact forces, are governed by Newton's third. Forces come in pairs. Forces are equal and opposite, and that also implies that momentum change is equal and opposite. Really? So the forces are equal but opposite. That's why I put a negative there. But I'm going to argue if it's the same collision for both vehicles, they must experience the collision for the same amount of time. The truck can't be in the collision for 2 seconds when the car is in the collision for 1 second, because if they're in the same collision, time is the same for both of them. Except, what's force times time?
Simple.
Yeah. In other words, I'm going to tell you that the impulse between the two of them is also the same magnitude, but one's positive, one's negative. It's equal but opposite. So, if the car above loses 20 units of momentum, what happens to the truck? But we didn't lose any momentum. The total momentum still stuck around. The total momentum during the collision did not change. It was just transferred from one object to another. This is profound. We're going to give that a law. And it's a consequence of Newton's third law. This is going to lead us to what we call the law of conservation of momentum. So, since momentum change is equal and opposite, the momentum for the system is not gained or lost. It's transferred from one object to another. Wait a minute, Mr. Dewick. Example 4. Turn the page. So let's have a big truck and a little car have a head-on collision. And we'll set the collision up so that at the end of the collision, they are at rest. If they're both at rest, what's the final momentum after the collision?
0.
So what was the initial momentum? 0. But Mr. Dewick, how can we say that that's the case? Because they were both moving. So there's the setup, Tato. If the final momentum was 0, the initial momentum was 0. Why? Because I just said the momentum for a system is not gained or lost. So if you end up with 0, you can't gain or lose anything. You must have started with 0 momentum. How can we say that? That's a good question. Draw a little line about 2/3 of the way over. Draw a line under after, because that's the after. Do you agree with me if they're both at rest after the collision, momentum final is 0? Okay. Before the collision, let's underline the word before, we have two objects moving. Yes? The truck and the car. How do I calculate momentum? Okay. So I'm going to write this. Before the collision, we have momentum of the truck plus momentum of the car. Can I use T for truck and C for car? And P for momentum. Alec, what did you say? How do I calculate momentum?
Mass times velocity.
So this is going to be mass of the truck, velocity of the truck, plus mass of the car, velocity of the car. You okay with that? Tato, what's the mass of the truck?
2400.
What's the velocity of the truck?
10 meters per second.
Plus, what's the mass of the car?
1000 kilograms.
What's the velocity of the car? Negative. Because it's in the opposite direction, and I've been telling you that direction is going to matter a lot more during this unit. What is... Oh, don't you get 24,000 plus negative 24,000? What was my initial momentum? Hey. Momentum was conserved. There was no change in total momentum. That's how we can say, if they ended at rest, that's how we can say, oh, the momentum at the beginning must have been 0. They just canceled out. If they didn't end at rest, that meant that one of the objects had more or less momentum. It's possible you could have a collision like that. It's possible right after the collision, the truck could keep going forward and be pushing the car backwards. It's possible right after the collision, the car could be going forwards and pushing the truck backwards. Those are really the three possibilities. The law of conservation of momentum. It says this: in any collision or explosion in a closed system, momentum is, here's the fancy word, conserved. That's a word in science that means you don't gain or lose anything. What you start with, you end with. Momentum is not created or destroyed, but only transferred from one object to another. This law can be written in several ways. In English, you write it as the total initial momentum of a system equals the total final momentum of a system. Of course, you know I'm never going to write it out in English. That's way too much writing. If you have two objects, you could say the momentum of the first object initially and the momentum of the second object initially equals the momentum of the first object later and the momentum of the second object later. And that equal sign right there is the collision or something. Alec, momentum is what times what?
Mass times velocity.
So instead of writing P, I could write m velocity plus m velocity initial equals m1 velocity 1 plus m2 velocity final. I tend to use this one because it's nerdy and clean and less writing. Now, what the heck does that one there mean? Does anybody know what that symbol is an abbreviation for?
Conservation.
Nope. Okay. Or, if you really want to read it short, total. The total momentum of everything initially equals the total momentum of everything afterwards. The sum of all the momentum you begin with equals the sum of all the momentum you end with. That's typically how I write the law of conservation of momentum. Why? Because it's short and it's nerdy looking. I start from there, and then, Sarah, I derive whatever I need to for my specific situation, and I'll walk you through how we do that. We use the law of conservation of momentum when there is a collision or an explosion. When there's a collision or an explosion. And so I wrote here, in short, we use C of M, conservation of momentum, when there is a jon. Is it a collision or an explosion? That's a job for conservation of momentum. There is a lovely example of the law of conservation of momentum. It's Newton's cradle. Let me pause the videos. So this now allows us to start to analyze car crashes. If any of you are going into the RCMP, if you get into crime scene investigation, accident investigation, here we go. Starts here. Example 5 says, find the missing velocity, magnitude, and direction. Is there a collision? Look at the picture. Is there a collision?
Yeah.
This is a job for conservation of momentum. Let me repeat that because some of you were zoning out. Matt, is there a collision? This is a job for conservation of momentum. What I do is I start out by writing this fancy schmancy thing, the sum of all the momentum beforehand equals the sum of all the momentum afterwards. By the way, that summation symbol, it's a Greek letter sigma, which looks like that, and then eventually you'll see it looks like that, and then eventually you'll see it looks like a capital M on its side. I get messier and messier and messier, but that's the trend. It just is going to get a little messier. So I do that one a little neater. Then I ask myself some questions. See the picture? Before the collision, what was moving? Mass A, mass B, both or neither? So I'm going to, stuck together before the collision or separate? Separate. So I'm going to write this. Momentum of A initial plus momentum of B initial. That was looking at the original situation. We'll do the first few in pictures, and then we'll start doing completely in words. But before the collision, it looks like these were both moving, and they were not stuck together. You okay with that? Mm-hmm. Then there was a collision. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? Stuck together or separate after the collision? Okay? If I mean stuck together, you'll see something like this stuck together, okay? So if they're separate, it's going to be momentum of A final plus momentum of B final. Alec, momentum is what times what?
Mass times velocity.
So I'm going to go like this. M A V A initial plus M B V B initial, wham, they collide, equals M A V A final plus M B V B final. I just took mass times velocity and ran it all the way through for each of those momentums, and I just made sure I had final, final, initial, initial, and A and B. What does this question want me to find? Look at the picture. Look at the after picture. What do they want me to find? What's got a question mark next to it? Looks like they want me to find that thing. Okay. How would I get this by itself? First, going to have to move that over by subtracting. And then that's going to give me M times V. How would I get the V by itself? Divide what? There you go. I'm kind of running out of room here, so I'm going to move over to here. If I heard you correctly, you're telling me the M-A-V-A initial would have just dropped down like a domino, and the M-B-V-B initial also dropped down like a domino. You said I would minus the M-B-V-B final, and then you said I'm going to divide by the mass of A. That equals the final velocity of object A. Ira, that looks right? Hey. And by the way, the equation you're going to use is this, which is I think the one I put on your formula sheet, and then we'll just adapt it to whatever situation by saying, hey, what was moving before? Hey, what was moving after? Hey, let's find what we need to find by getting it by itself, using mass times velocity. All right, here we go. So V final of object A is going to be mass A, 1,000. What was VA initial from the picture?
10 meters per second to the right.
Plus mass B, 2,000. What was VB initial? Don't say 2 because it's not. Has to be. See it? Then I have a minus mass B, which is 2,000 again. What was VB final? 4? Divided by the mass of A. How fast is car A moving after this is over? We're going to go magnitude and we'll go a direction. Which way did we let be positive? Left or right?
Right.
Okay, so if we get a positive answer to the right, if we get a negative answer to the left? Is this a fraction? More than one thing on the top, brackets around the top. Don't need brackets around the bottom. You get -2? Or am I wrong? Or 2 meters per second left. So let's visualize this particular collision. Car B is the bigger car. Car A is the smaller car. They start out heading towards each other. And then after the collision, car B bounced to the right, car A bounced backwards to the left. Boom, they bounced apart off each other. That doesn't violate the laws of physics or anything. I'm good with that. B. What's B want me to find? Looks like how fast car A was going to begin with, which is probably in a crime scene investigation, what you'd be much more interested in. Is there a collision?
Yeah.
This is a job for conservation of momentum. It's going to look like this. The total, or the sum, of all the momentum before the collision equals the total, or the sum, of all the momentum after the collision. before the collision, what's moving? Mass A, mass B, both or neither? Stuck together or separate? Okay. Really what I'm saying is, how much momentum did we start out with? What was moving? So I'm going to go momentum car A initial and momentum of car B initial. Separate. You okay with that? Bam! They collide. After, really, Mr. Dewick? Every collision? Maybe. After the collision, what's moving? Car A, car B, both or neither? Both, stuck together or separate? So momentum A final and momentum B final. I also noticed some changes in directions in the arrows, so I'm going to be really, really careful. I think here, previously I said for impulse I tend to let final be positive. Here I think I'd let to the right be positive and to the left be negative because there's lots of changes going on here, and that I think Ange is going to be easier to track. Yes? Alec, momentum is what times what?
What?
Momentum is what times what?
Oh, mass times.
This is going to be your cue for a little bit, okay? So this is going to be mass A V A initial plus mass B V B initial equals mass A V A final plus mass B V B final. I scrolled down. What were we trying to find? How will I get that by itself?
Divide M and M.
Not yet.
Subtract MB, VB.
First I'll minus the MB, VB initial, and then I'll divide by M. Are we okay doing that all in one fell swoop? So I think I'm going to get this. Come on. VA initial, it's going to be the MAVA final would just drop down like a domino, and the MBV, I forgot to put, you know what, I wrote V final final. I should have written VB final, shouldn't I have? VB final, and then you folks said I'm going to minus the MBVB initial and divide by mass. Which mass? Mass of A? Okay. Mass of A was 1,000. What's the final velocity of mass A? I've scrolled down.
2 meters, 2 seconds to the left.
So 2 or negative 2? Negative 2. Plus mass B is 2,000. That I still have on my screen. What was the final velocity of mass B?
4.
Positive or negative?
Positive.
Okay. And then minus mass B, which is 2,000. What was the initial velocity of mass B?
Negative 3.
Negative 3? To the left? Yeah. 1,000. And this is VA initial, if I recall. What do you get? 12? Direction. Because I got a positive answer. Now, this is the velocity the split second after the collision finishes. Then what would happen? Friction from the pavement would bring you to a stop. Friction from the pavement would bring you to a what? So V final after the collision would be 0. You would measure the length of the skid marks. That would give you a distance. We now know how to calculate friction. It would be mu times the normal force. I don't know the normal force. It would be the mg of the car, and you would know the mass of the car because you could look that up. You could actually calculate what the acceleration was from the force of friction, and now you would get V final at the end of the collision, and then you could work your way backwards and figure out V initial before the collision. That's a much more realistic way of how it's done. You might recall near the beginning of the year we did a question where I had the phone pick up the sound of the screeches because you didn't have all the skills to handle it. Now you could. C. Is this a collision? This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. And again, Kiana, you notice I'm being careful with my vector signs. I won't take marks off if you forget to put the vectors on, but the reason I'm being so careful, I'm reminding myself, I better be paying attention to direction here. In particular, I've already glanced part A. It looks like there's a change in direction at the initial part. Part B, okay. Before the collision, what's moving? Mass A, mass B, or both? Stuck together or separate before the collision? So I'm going to have momentum of car A coming in, initial, and momentum of car B, initial. They collide. After the collision, what's moving? Car A, car B, both, or neither? Stuck together or separate? Momentum of both. Final, because they're stuck together. Is that a pretty reasonable shift? Okay. Momentum is what times what? Alec? So this is going to be mass A, velocity A initial, plus mass B, velocity B initial. When they collide? Both. Hey, how about mass A plus mass B, V final? I think that would be the momentum of both stuck together, wouldn't it? Yeah. You treat it like one big uber mass. What am I trying to find? Trying to find that thing? How would I get that by itself? Minus MB VB. And then? Oh, there you go. Jason is correct. He said, okay, if you want to get the VA initial by itself, first the MA plus MB V final stays where it was. It drops down like a domino. And then I would minus the MB VB initial and divide by which mass, Jay? M of A. Yeah. All right. Plug and chug time. The incoming velocity of object A. Mass of both, is it 6,000? The cars have changed. 2,000 plus 4,000, 6,000? Do you mind if I go straight to that in my head? V final, I've scrolled down. What was V final? Positive or negative? Positive, okay. Take away mass of B, which is 4,000. What was V initial of object B? Negative 3 divided by mass of A, which is 2,000. How fast will both of these vehicles move off together? We're looking for VA initial, sorry. How fast was object A coming in at? I think I can do this in my head. It's going to be 30,000 plus 12,000, 42,000, 26? No. 21? Yeah. 21? Is that right? Yep. I'm going to date myself. I'm going to tell you how old I am. When I was a little kid, 8 years old, 7 years old, back when you didn't realize that you shouldn't break things that parents bought for you, we used to do something that we jokingly called ghost riding with our bicycles. Do they still call it that? Jason smiled. And what it was is you would get going really fast, and then you would jump off the bike and run alongside it while it would keep going, hopefully in a straight line. We said you were ghost riding. And then if you were really good, you would try running and jump back on again before it fell down. Well, I think situation D is sort of like that. This person is biking along on their bike. Whoa! Something happens. And we have that. Oh, you know what? Before the collision, stuck together or separate? After the collision? Ah, okay. This fits in our model as well. This is sort of a collision. Actually, as opposed to a collision, since we're coming apart, that's an explosion. As I said, momentum works best when there's a jeune. So, the sum of all the momentum beforehand equals the sum of all the momentum afterwards. Before the collision, what's moving? Mass R, mass B, both or neither? Both, stuck together, or separate, stuck together. So we're going to go momentum of both initial. Boom! There's an explosion. It's kind of a slow motion explosion, but it's an explosion. After the collision, both and separate. Yes? It looks like we're calling R for rider, B for bike. So momentum of R final plus momentum of bike final. And it looks like they want me to figure out how fast the bike is going to be going. Now, before we go, let's see if we can get a gut instinct of what the answer is going to be. After I jump off the bike, will the bike speed up or slow down? What's happened to my velocity afterwards? So I'm going to ask you the same question. I'm just going to phrase it differently. What's happened to my momentum afterwards? So if I lost, what Tato? If I lost momentum, what does the bike have to do? Gain momentum. Did the bike gain mass?
Nope.
Then it must have gained velocity. In other words, I'm telling you right now, my answer better be bigger than 5. Otherwise, I've messed up. So you can, as you get good at these max, kind of have a gut instinct of, well, is my new answer going to be bigger or smaller or, you know, close to? Okay. Alec, momentum is what times what? So this is going to be mr plus mb v initial equals mrvr final plus mbvb final. What are we trying to find? This puppy here. I think it's going to be minus that to that side and then divide by mass of B. Okay, so I'm going to have mass of R plus mass of B V initial minus mass of R V R final, all divided by mass of the bike. That equals the final velocity of the bike, which I'm hoping gives me an answer that was bigger. Let's see. V bike final is mass of R plus B 80, V initial 5, minus mass of the rider 60, V final 2 or negative 2?
2.
What if I jumped off backwards? How would that speed compare to this speed?
That would be much faster.
Yeah, it would blend even, because now I have a negative momentum. The bike's got to pick up even more momentum. But for now, 2 divided by mass of the bike, 20. Is that right, Mr. Duke? I interrupted my thought process. That looks right. I think I can do this in my head. It's going to be 400. Take away 120, which is 300, 280, 14?
Yeah.
Now, in real life, the bike would slow down, so if I kept running, I could probably catch back up to it and hop back on. And that's what we tried doing as kids. We called it ghost riding. We didn't have video games. We played outside. We're going to continue this next class, but for now, as a head start, you can try number 1. You can try number 2. You can try number 3. This is not homework. I'll give you time next class, but there's a few minutes left. 4 is good. You can see if you can handle a little Calvin and Hobbes. We'll pause there. Okay.